Hi folks, I'm attempting to do a video lecture today on extinction and the Rescorla Wagner model. I picked these two topics. Well, first of all, I'm inviting you into my home because they say this is supposed to help with online learning, give you a bit of a feeling of intimacy doing a videotape from my home. So with that said, I'm going to also try and explain extinction as well as a bit of the Rescorla Wagner model, since students can get a little bit freaked out by math. So I'm here in my home. I'm going to quit focusing on myself now and show you some other things, one of which is my dog. Zach, turn around and say hello. This is my dog, Zach. He is going to be the impetus for my example today because it can really confuse some people. Oh, before I get into the Rescorla Wagner model, actually, here I go back to myself, I wanted to just briefly mention extinction because this is a concept that's changed a bit over the last 10 to 20 years. So you may hear about it differently from some people. So extinction, and again, I'm doing this video kind of assuming you've already read the chapter and I'm trying to explain things in a little more detail. So if you haven't read the chapter yet, you might want to stop this video, go read it, and then come back to the video. So extinction, a lot of times people would think of as unlearning. So getting rid of learning, forgetting. But extinction is not forgetting. In fact, there's more and more evidence that shows that extinction, that learning that was originally there, stays there. The spontaneous recovery, particularly when it comes to treating things such as phobias and other anxiety disorders. Extinction is not an unlearning so much as putting new learning in place of what was previously learned, or at least attempting to. Because one of the difficulties is once something is learned very well, it actually stays there. And as much as we'd like to be able to extinguish it sometimes, we can't. So okay, that was going to be my brief thing about extinction. The book mentions it, but I don't think goes into enough detail. When we get to emotion, it'll come back up again. So on to the Rescorla Wagner model that sometimes does really frighten people. What I've done here is I've got a little piece of paper where I'm discussing some of the concepts. Don't worry about jumping ahead. Stick with me. I just wanted to go over again some of the things the book has already said. First, I want to define what W is. W is an associative weight. So how well the conditioned stimulus predicts the unconditioned stimulus to begin with. Now I already mentioned I'm going to use my dog as an example. Let's say you have a brand new dog who's never been to your home before, never heard your doorbell before, and never heard any doorbell like it before. Doorbell goes off, the dog has no idea what that doorbell means. So the association between the doorbell and somebody's at the door for that dog has a weight of 0. In other words, that doorbell doesn't predict a thing for that dog right now. On the other hand, there's my dog, who I've had for over 10 years now, and any doorbell he has learned means that somebody's at the door. He hears the doorbell, he goes nuts, and I'm going to really hope nobody rings the doorbell while I'm videotaping. So for him, the sound of the doorbell predicts somebody at the door 100% of the time. So for him, the associative weight of doorbell is 100. Okay, so weight of doorbell could be defined for one dog maybe 0, for another maybe 100. When a dog's still in the learning process, it's going to be somewhere between 0 and 100. So for my dog, it's 100. Now there are other things that also predict if somebody's at the door. Knocking on the door. Sometimes my doorbell doesn't work or somebody doesn't see it. So we could have another associative weight for something like a knock. For my dog, again, knock means somebody's there. So conditioned stimulus is the knocking sound, unconditioned stimulus is somebody's at the door. For my dog, that weight is also 100. But again, imagine there's a dog that has never heard a knock on the door, never heard the doorbell ring. The weights for that animal would be 0. And then in the learning process, it's going to be somewhere between 0 and 100. Now, prediction error is the difference between what actually happened when that stimulus occurred, that conditioned stimulus occurred, and what was expected. Oh, I'm sorry, the actual unconditioned stimulus and what was expected to occur for the unconditioned stimulus. I'm not sure if I messed that up. But here you can see we're saying it's the actual unconditioned stimulus. So when the doorbell rang, was somebody at the door or were they not? So the actual unconditioned stimulus is either going to be a 0 or 100. There's no in between for the actual unconditioned stimulus. It's always either a 0, the unconditioned stimulus didn't occur, or 100 where it did happen. So again, in my dog's case, the doorbell rings and either somebody is not there, we open the door, nobody's there. Okay, that doesn't happen too much. Or we open the door and somebody is there. So the actual then would be 100 if somebody is actually at the door. And that would be, the prediction error is based on both the actual and the expected. So the expected was the sum of all the weights for those conditioned stimuli that occurred in terms of whether the dog expected somebody to be there or not. So for my dog, the doorbell going off has an associative weight of 100. So doorbell goes off, his expected US is 100. Now, why do we not just say expected US is the weight? Well, it's because it's the sum of all the weights that happen to occur on that trial. So if you've got a dog that's learning about the doorbell and knocking, you would take the weight for the door and the weight for the knock if they both occurred. So my dog example, the doorbell rings, the weight is 100. If somebody rings the doorbell and knocks, we add the weight of the doorbell ring 100 to the weight of the knocking 100. It actually gets maxed out at 100. That's the most you can get. But if my dog was just learning that doorbells and knocks both mean people are there, and the weight was closer to 20 for doorbell and only 10 for knocking because people don't knock as much, we'd add the weight of 20 for doorbell to the weight of knocking for 10, and we'd get an expected occurrence of 30. Okay, I'm getting beyond myself here though. But basically the idea is what really happened versus what did happen. To get the prediction error, you actually just take the actual occurrence, so that's either going to be 0 or 100, minus what the animal expected to occur, which was the sum of all the weights of the conditioned stimuli that occurred on a trial. Okay, so prediction error, if the actual unconditioned stimulus, let's say the doorbell rang and somebody was at the door. The actual is 100, and in this case with my dog, the expected was 100. So 100 minus 100 is 0. In other words, my dog predicted it dead on, no prediction error whatsoever. He's actually not going to have any change in weight based on his prediction error at all. So there's no learning occurred there because he was already maxed out on learning and he didn't have any prediction error. If, on the other hand, the doorbell rings but nobody's there, the actual US is a 0, but his expected US, having been a fully trained dog, is 100. So 0 minus 100 is negative 100. So he has a prediction error of negative 100. Okay, now what happens? Now hopefully the dog will learn from this experience, and how he learns, or anybody learns, is based on the amount of that prediction error as well as the animal's learning rate. Some animals learn quickly, some animals learn a little bit slowly. My dog's a little on the dumb side, so his learning rate's a little bit lower. So, first of all, remember, if his prediction error was 0, if he got it right, nothing's going to happen because the change in weight is based on prediction error and learning rate. Beta is the learning rate. That is some constant that is just, you have to be given an example of this because we don't know what somebody's learning rate is. Something we have to determine, or somebody has to tell you this is the hypothesized learning rate. and you multiply the learning rate times the prediction error. Well, if my dog's not very smart, he's going to have a small learning rate. If his prediction error was 0, no matter what, times 0 is still 0, and there's not going to be any change in the weight of that stimulus. Okay, so no learning occurred. If, on the other hand, he went to the doorbell rings and nobody's at the door, he's got a large prediction error, a 100 prediction error. However, if he's got a small learning rate, let's say he's not very bright, let's say he only learns at a rate of 0.01, we're going to multiply that by his prediction error of 100, we're actually only going to get a change in learning rate of 10 at most. So that's our delta W for the change in the weight for the doorbell predicting whether somebody's going to be at the door. So then to actually apply that to what his original rate was. So his original rate was W of doorbell was equal to 100, but now his change in W after that one experience that the doorbell rang and nobody was there, is just going to make it go down by 10. Oops, I've got a little bit of a sign problem here because this was negative 100, so this should be negative 10. So 100 minus 10 means now the doorbell predicts somebody's at the door only 90% of the time. So his learning, his strength of associative learning or associative weight has now gone down to 90. So next time the doorbell rings, his expected US is only going to be 90. Now, if somebody also knocks on the door, we have to add together the weight of knocking for my dog plus the weight of the doorbell. So we've just reduced his doorbell weight by 90, or down to 90. But all of the other cues are going to get put in there together to help him predict whether somebody's really at the door. So that's how learning occurs. So if I eventually want my dog to stop barking every time the doorbell rings, I have to keep ringing the doorbell and have nobody be at the door. Do it over and over again. The slower his learning rate is, the more times I have to do it. But eventually, he would learn to quit barking at the doorbell. Now, of course, eventually people are going to ring the doorbell and be there. So that means his change in W will go back up. Because as his expectation goes down, then if we get an actual US where somebody is at the door, that means actual US is 100. If his expected is lowered, let's say it's at 90, then we have a prediction error of positive 10. Okay, and his change in weight is going to be based on that learning rate of beta that I gave you in my example is 0.01 times his prediction error of 10. So he's going to learn a little bit more to expect somebody back there. So you can go over iteration of every time that stimulus occurs, looking at whether it actually occurred, whether there was an actual outcome of the unconditioned stimulus in comparison to what the animal expected, and look at the learning rate. So I hope this video helped explain it. The math, the most complicated math in here is multiplication. Don't forget your sign, like I did. So dropping that negative can actually make it look like an animal is learning as opposed to, is getting a stronger association as opposed to decreasing that association. So don't forget the sign. It's important. And this is going to be important when you do your concept check questions next week. So take a look at the book again, go over some of the examples they've gone over in the book, and the book does a better job than the first version of the book did in terms of explaining this, but don't freak out and run through some examples where they have answers in the back. Okay, I hope you've all enjoyed meeting my dog. Zach, do you want to say goodbye?